In this video, we discuss learning outcome number 5 for lesson 9.2, which is about alternate methods for testing a claim about two population means when the sample data collected are from two independent random samples. Now, we've already talked about the p-value method, the critical value method, and the confidence interval method in the case when the population standard deviations were unknown and not assumed to be equal to each other. We're not actually going to do any examples when that is not the case, but we are going to outline modifications to those methods that we've already studied that are appropriate when those conditions aren't met. We're actually going to look at 3 additional cases in this video. So here's the first of our 3 cases. If the population standard deviations sigma sub 1 and sigma sub 2, are unknown, but we have reason to assume that they're equal, what we'll do in that case is we'll do something called pooling the variances. Here, the requirements are the same as those discussed when the population standard deviations were unknown and not assumed to be equal. We're just saying now that we're assuming that they're equal. The difference here is not in the requirements, but in the formulas. The formulas are going to change now, and they will be computed in terms of what's called the pooled estimate of that population variance, which is denoted by S sub p squared. We're going to use this whenever it's appropriate to assume that those two population standard deviations are equal to each other. One example of this would be when randomly assigning subjects to treatment and placebo groups. In that case, the samples are drawn from the same population, so it makes sense to say or to assume that those standard deviations would be equal to each other. So that's one example. Now, one advantage of pooling the variances like this is that the number of degrees of freedom is a little higher. So in that case, the hypothesis test will have more power and our confidence intervals will be a little bit narrower. Having a narrower confidence interval is a very good thing, because basically what that's saying is that we're getting closer to estimating the true value of mu sub 1 minus mu sub 2 because we have less error around it. That margin of error is smaller. So this is a great thing in that it makes our margin of error smaller. So it gets us closer to that true value of what we're trying to estimate, but it's only appropriate, if it is appropriate, to assume that the population standard deviations are equal to each other. Now, in this case, our test statistic is given by this formula. Notice that it's almost identical to the test statistic that we used before, but before we had S sub 1 squared here and S sub 2 squared here. So those were the sample standard deviations squared, so sample variances for the first sample and the second sample. But now, instead of doing that, we're saying we think that those population variances or population standard deviations are identical to each other. If they are identical to each other, then these two values should be the same value. The problem is we've got 2 samples and we have 2 sample standard deviations. We don't have one common value for both standard deviations. The way we find that common value is we compute this quantity here. This is called the pooled estimate of the population variance, or the pooled sample variance. That's why it has S sub p for pooled sample variance. And it's basically just a weighted average of the 2 sample variances that we had. In the numerator, you've got the sample size minus 1, so that's the appropriate number of degrees of freedom, times that first sample variance. And then we add the sample size minus 1 times the second sample variance. And then we divide by the number of degrees of freedom for, or what would traditionally be the number of degrees of freedom for that first sample, which would be 1 less than the sample size. And then we add the 1 less than the sample size for the second sample, and those are both going into the denominator. So this is our pooled sample variance, and we use this in place of S sub 1 and S sub 2 here. Again, it's just a weighted average of those 2 sample variances for each sample. And we're saying if we take this weighted average, that is a good estimate of the common value of S sub 1 and S sub 2, or the common value of sigma squared, the population variance squared, um, given that S sub 1 and S sub 2 are the population, or excuse me, the sample standard deviations for each of those two samples. Now here, the number of degrees of freedom is not the sample size minus 1, it's the first sample size plus the second sample size minus 2. Because again, it's like you're choosing members for a team. If you've got um, yeah, n sub 1 kids on this team, and you're choosing members for a team, you get to choose the first n minus 1 of them, but you don't get to choose the last one. And the same is true for the second sample. So we just add those two amounts of degrees of freedom together to get the total number of degrees of freedom for this hypothesis test. Okay, so that's our test statistic with the number of degrees of freedom. As long as you use that, everything that we talked about previously for the p-value method and critical value method can be applied here with this test statistic t and this number of degrees of freedom. Now, if you want to construct a confidence interval for the difference between those two population means, when we assume that the population standard deviations are equal to each other, we're just going to use these formulas here. And again, everything is pretty much exactly the same. The only thing that is changing is that estimate of the standard deviation of the sampling distribution of x sub 1 bar minus x sub 2 bar. And that estimate is changing because we're assuming that those two population standard deviations are equal to each other. So we're saying if they are equal, what is a common value for those? What is a common value for that population variance? And we're saying that the best estimate that we have of that value is this pooled sample variance, which is this weighted average of the two sample variances that we have for our two samples. And the number of degrees of freedom is the same as it was last time. Okay, so that is our first situation, and it's actually a relatively common situation because often we've got a treatment group and a placebo group, just for example, where we're pulling from the same population. So it actually makes sense to assume that the population standard deviation would be the same. Now, this second situation is very uncommon, almost so uncommon that we don't mention it. But I will still mention it for you. Let's say that both population standard deviations are known. This is just almost never happens. In this case, the requirements are exactly the same as before, except this time we're actually allowed to know the population standard deviations. In that case, you're just going to replace, the sample standard deviations S sub 1 and S sub 2 with the population standard deviations sigma sub 1 and sigma sub 2. And then in that case, it's appropriate to use the standard normal distribution and z-scores rather than the student t distribution and t-scores. So our test statistic in that case is a z-score, and it's computed in almost exactly the same way as that test statistic t was computed. But instead of having an S sub 1 here and an S sub 2 here, you've got sigma sub 1 and sigma sub 2. And then our confidence intervals can be found by evaluating this. And again, the standard deviation is that same standard deviation in the denominator. And instead of having a t-score here, we've got a z-score. So everything is pretty much the same. But now you're working with z-scores. And because you're working with z-scores, you can look up probabilities in table A2 or tables of z-scores using the standard normal distribution, as opposed to having to worry about degrees of freedom and different shapes of student t distributions, as we would have to when the population standard deviations are unknown. But again, it's very rare to use these formulas because most of the time we don't know the population standard deviations, especially if we're trying to make an estimate of the difference between the population means. In that case, it's very rare to know the population standard deviations. Okay, so that was our second situation, which is very rare and uncommon, and you're probably never going to use those formulas. But I wanted you to be aware that that's how we would handle that situation if we came across it. Now, the last situation is when one of the population standard deviations is known and the other one is unknown. And here we're going to do the same thing. We're just going to use the same methods from before, but we're going to make a few changes. If the first population standard deviation is known, rather than using the sample standard deviation, use the population standard deviation, of course. That makes sense. And then the number of degrees of freedom is given by this formula rather than any of the other formulas that we've discussed. Once you have that number of degrees of freedom, you're going to come up with that student, or you're going to use the student t distribution again. You're going to come up with a test statistic t. You're going to use critical values from a student t distribution as well. So everything is pretty much the same. The formulas just change a little bit if you happen to know one of the population standard deviations and you don't know the other one. Now, in practice, the methods that we talked about earlier are the methods that you're going to use. Most of the time, there's no reason to believe that those population standard deviations are equal to each other, and we don't know either of the population standard deviations. So the methods that we discussed in the last 3 videos, that was 9.2.2, 9.2.3, and 9.2.4, are the appropriate methods almost all of the time. The only one of these 3 additional situations that is relatively common is that first case when we might assume that the population standard deviations are equal to each other because the 2 groups are being pulled from the same population. But even then, we should confirm that those standard deviations are equal to each other using some methods of analysis that are sort of beyond the scope of our class. So that's it for those 3 additional situations. We're not going to do any examples, but I just wanted you to be aware of them. I will see you next time to discuss a little bit more statistics.